Welcome back to another episode of Tech Talk Today. I'm your host, Your Name, and today we're diving into the fascinating world of MapReduce and distributed file systems with a special focus on Hadoop's implementation known as HDFS. Whether you're a seasoned data engineer or just curious about how big data is processed, this episode is filled with insights that will shed light on the power and efficiency of these technologies. Let's start by unpacking what MapReduce actually is. At its core, MapReduce is a programming model designed for processing large data sets across distributed clusters of computers. It's like a powerful tool that breaks down big tasks into smaller, manageable pieces. Similar to how Unix tools work, this approach allows for data processing to happen in a parallelized manner. Imagine you have a massive set of input files. The first step in a MapReduce job is to read these files and break them down into records. For instance, if you're analyzing web server logs, each line of the log file can be treated as a separate record. This is where the mapper function comes into play. The mapper extracts key value pairs from each record. In our weblog example, it might pull out the URL as the key and leave the value empty. Once the mapping is complete, the next phase involves sorting all these key value pairs by their keys. This sorting is crucial because it sets the stage for the reducer function, which processes the sorted data. The reducer takes these sorted pairs and combines values that share the same key. So, if multiple records correspond to the same URL, the reducer can easily count how many times that URL was accessed. Now, you might be curious about how this all fits into the broader picture of distributed systems. That's where HDFS, or the Hadoop Distributed File System, comes into play. HDFS is a distributed file system that enables the storage and access of large datasets across many machines. It operates on the shared nothing principle, meaning each machine in the cluster is self-sufficient and doesn't depend on a centralized storage system. In HDFS, files are written once and in a sequential manner, which means you can't modify existing parts of a file. This design choice simplifies the data processing model and enhances performance, especially when dealing with large volumes of data. A central server, known as the name node, keeps track of where each file block is stored across the cluster, creating a cohesive file system that utilizes the storage capacity of all connected machines. One of the standout features of HDFS is its ability to schedule computing tasks on the same machines that store the data. This is particularly beneficial when network bandwidth is a concern. By processing data locally, you minimize the need to transfer large files over the network, which can often become a bottleneck in data processing workflows. Now, let's dive deeper into the MapReduce process itself. As we mentioned earlier, a MapReduce job consists of two main functions, the mapper and the reducer. The mapper processes individual records and generates key value pairs, while the reducer aggregates these pairs based on their keys. This separation of concerns is what allows MapReduce to efficiently handle massive datasets. When you set up a MapReduce job, you typically implement these functions in a conventional programming language, like Java. In Hadoop, both the mapper and reducer are Java classes that adhere to a specific interface. This design allows developers to focus on the logic of their data processing without getting bogged down by the complexities of parallelization. The MapReduce framework takes care of distributing tasks across the cluster and managing data movement between machines. Let's talk about the data flow in a MapReduce job. When you initiate a job, the MapReduce scheduler assigns tasks to different machines based on the input data. Each input file is treated as a separate partition, which can be processed independently by different mappers. This parallelization is key to the efficiency of MapReduce. Once the mappers finish their tasks, the next phase is known as the shuffle. This is where the output from the mappers is sorted and sent to the appropriate reducers. The reducers then merge these sorted outputs while preserving the order, ensuring that all records with the same key are processed together. This process is crucial for generating accurate and meaningful results. However, it's important to note that the capabilities of a single MapReduce job can be somewhat limited. For example, while you can easily count the number of page views per URL, determining the most popular URLs would require a second round of processing. This is where chaining multiple MapReduce jobs comes into play. By configuring the output of one job to serve as the input for the next, you can create a workflow that handles more complex data processing tasks. But here's the catch. Hadoop's MapReduce framework doesn't inherently support these workflows. Instead, you have to manage this chaining through directory names in HDFS. Each job must be set up to write its output to a designated directory, which the subsequent job will read from. This design is akin to a sequence of commands, where each command's output is written to a temporary file rather than a direct pipeline of processes. To manage these dependencies between jobs, various workflow schedulers have been developed for Hadoop, such as Oozie, Azkaban, and Airflow. These tools help automate the execution of chained jobs, ensuring that each job starts only after its dependencies have completed successfully. In conclusion, MapReduce and distributed file systems like HDFS are powerful tools for processing large datasets efficiently. By breaking down tasks into smaller pieces and leveraging the capabilities of distributed systems, you can unlock insights from data that would otherwise be too cumbersome to handle. Whether you're analyzing weblogs or processing complex datasets, understanding these concepts is essential for anyone working in the field of data science or engineering. Thanks for tuning in to this episode of Tech Talk Today. If you enjoyed our discussion, be sure to subscribe and join us next time as we explore more exciting topics in technology. Until then, keep learning and stay curious.